You're sitting there, reading this, thinking you're standing still. Zero motion through space, right? But are you moving through time? Of course you are. 1 second per second, we say. But what does that even mean? How fast is 1 second per second? Is that a speed? Speed of what? We say time passes, but that's just words. We measure it with clocks, but that doesn't explain it. The truth is, you're always moving at exactly the same speed through space-time. Not just space, but space-time is one thing. Light speed, always. And when you move through space faster, you must move through time. Suppose I ask differently. What do we mean by speed? Speed is distance divided by time. Miles per hour, meters per second. Movement through space over some duration. But speed through time? That would be time per time. The number comes out to just 1 second per second. It sounds circular, meaningless. And yet, there's something there. Because you do move through time. Every second that passes, you advance 1 second into the future. That's motion, isn't it? Motion forward along the time axis. But how do we measure it? What's the speed? Against what reference? The essential point is this. Space-time is not two things. It's one unified thing, one four-dimensional fabric. And you're always moving through it at one fixed speed, the speed of light. Always. 300 million meters per second through space-time, not through space alone. When you're sitting still in space, all that motion goes into the time direction. You're traveling through time at maximum speed, light speed, c, aimed entirely at the future. Your velocity through time is c. When you move fast through space, some of that motion diverts there. A trade-off must happen. Total motion through space-time stays c, but it splits between space and time. Think of it like walking. If you walk straight north at 3 miles per hour, that's all north, no east. But if you turn and walk northeast, you're still walking at 3 miles per hour total, but now it's split. Less north, some east. The total speed stays the same, just redirected. Well, not exactly like that. The geometry is different, stranger. In ordinary geometry, if you go 1 mile north and 1 mile east, you've traveled about 1.4 miles total. Pythagorean theorem. In space-time, the math has a minus sign. Motion through space subtracts from motion through time. But the principle holds. You have a fixed total speed through space-time. When you redirect some toward space, you must lose some from time. Which means when you're standing still in space, you're not standing still at all. Zero motion through space means maximum motion through time. You're traveling through time at c. Full light speed, just aimed at the future. Every atom in you, every particle, racing forward through the time dimension at 300 million meters per second. Not metaphorically, literally. That's your velocity through time right now. But why that speed? Why c specifically? Why not some other number? Why not 1 billion meters per second or 1 meter per second? Here's the thing. We discovered it backwards. We found light travels at a fixed speed first. Only later did we realize that speed is fundamental to spacetime itself. In 1887, two Americans, Michelson and Morley, set up an exquisitely sensitive experiment. They measured the speed of light traveling in different directions. They expected it to go faster when the Earth was moving toward the light source, slower when moving away. Like running into the wind versus away from the wind, you'd measure different wind speeds depending on your motion. Light should work the same way, they thought. Maybe a few kilometers per second difference. Light didn't care. Same speed always. No matter which direction they measured, no matter how the Earth was moving through space. 300 million meters per second exactly, to within their measurement precision, which was good, no variation. This should not happen. They checked their apparatus. They checked again. They refined the experiment, tried different times of year when Earth moves in different directions. The result held. Light speed is constant. Most people ignored it. Strange experimental result, they thought. Maybe some mistake. Or some mundane explanation they hadn't thought of. I took it seriously in 1905. If light always measures c, no matter how you move, then space and time themselves must adjust to make that work. Moving clocks must run slow. Moving rulers must contract. Not because something happens to the clock or ruler, because space-time geometry requires it. The very structure of space and time enforces this constancy, and here's what that means. Light speed isn't just unusually fast motion through space. It's all motion through space, and zero through time. A photon doesn't experience time at all. From its perspective, the universe is frozen. Imagine, from the photon's point of view, it exists and arrives simultaneously. No duration between emission and absorption. The journey that takes years by your clock, that crosses light years of space, takes zero time by its own clock. If a photon could think, it would say, I was emitted from that star and absorbed by that eye in the same instant. We can prove this affects real particles, not just light. A photon leaves a star. It travels 1,000,000 light years to reach your eye. For you, watching from Earth, 1,000,000 years passed while that photon was in flight. The star might have died in the meantime. Civilizations might have risen and fallen. For the photon, zero time. It doesn't age, doesn't decay, doesn't experience duration. Not very little time. Literally zero. Why? All its speed is through the space dimension. 300 million meters per second through space. None left for the time dimension. It's moving through time at zero speed. Time, from the photon's perspective, doesn't pass. This isn't metaphor. This is geometry. The mathematics of space-time, worked out precisely, gives exactly this result, which means you're the opposite of a photon. You're moving through time at maximum speed because you're moving through space at minimum speed. You're mostly stationary in space, so you're moving at maximum speed through time. Move faster through space? You must slow through time. The trade-off is mandatory. The total motion through space-time stays fixed at c, and we can measure this. We have. Many times. Take muons, subatomic particles created when cosmic rays hit the upper atmosphere. They're created about 15 kilometers up. They should decay in about 2 microseconds. That's their half-life, measured carefully in laboratory experiments. At the speed they travel, close to light speed, they should cover about 600 meters before half of them decay. They shouldn't reach the ground, but they do. They reach the surface in abundance. We detect them all, the time. Why? Because when moving near light speed, their clocks run slow from our perspective. What's 2 microseconds for a stationary muon in a lab becomes much longer for a muon moving at 99% of light speed. Their time slows down. To them, they live their normal 2 microseconds. To us, watching them zoom past, they last much longer, long enough to reach the ground. Or, from their perspective, we're aging fast. The Earth is rushing up at them at near light speed. To the muon, we're the ones time dilated. Same mathematics, different frame. Both perspectives equally valid. The twin paradox. One twin travels fast in a spaceship, turns around, comes back younger. This is real. Measured with atomic clocks on airplanes, measured with particles in accelerators, used every single day in GPS satellites. The satellites orbit at about 14,000 kilometers per hour, moving fast. From their perspective, time passes normally. From our perspective on the ground, their clocks run slow. They experience less time. We have to correct their clocks by about 7 microseconds per day due to motion. Actually, gravity makes them run fast by about 45 microseconds per day. So the net correction is 38 microseconds per day fast. Both effects, motion and gravity, are real and measured. If we didn't account for them, your GPS would be off by kilometers within a day. This is not theory. This is engineering. Every GPS satellite proves relativity thousands of times per second. Well, I mentioned gravity affects it too. That's related. Gravity is space-time curvature. Mass bends space-time, and that bending changes how time flows. Near a massive object, time runs slower. That's another story, but it's part of the same picture. Space-time is unified structure, not separate space and time. But here's the question that might bother you. Why can't you tell you're moving slower through time when you move fast? Because your clock slows with you. Every process in your body, chemical reactions, electrical signals in your neurons, quantum transitions in your atoms, all governed by the same space-time geometry. From your reference frame, 1 second still feels like 1 second. Of course it does. You're measuring time, with processes that slow down at exactly the same rate. You can't notice your own time dilation any more than you can taste your own tongue. The measuring stick changes along with what's being measured. Only comparison with a different reference frame reveals the difference. Only when the traveling twin returns and compares watches with the twin who stayed home do they see the discrepancy. It's like asking if you're moving through space right now. Sitting in your chair, you feel motionless. The floor isn't rushing past you. The walls aren't moving. Motionless. But the Earth is rotating at about 1,000 miles per hour at the equator. The Earth is orbiting the Sun at 60,000 miles per hour. The Sun is orbiting the center of the Milky Way at 500,000 miles per hour. The Milky Way is moving through space relative to other galaxies at over 1,000,000 miles per hour. Are you moving or not? The question has no absolute answer. You're motionless relative to your chair, moving fast relative to the galactic center. Motion through space is relative. There's no absolute rest frame, no cosmic standard of truly still. Same for motion through time. Your rate of passage through time depends on your motion through space, relative to other objects. No absolute time rest frame. No universal clock ticking at the true rate. But there's something deeper here about why it's light speed specifically. Why that number? Why is the maximum space-time speed exactly the speed that light travels? That seems like quite a coincidence. Why should light, of all things, define the fundamental structure of space-time? It's not a coincidence. It's backwards. Light travels at c because c is fundamental to space-time. Light has no mass, so it can't go slower than c through space. It has no choice. Anything with mass can't quite reach that speed through space, would need infinite energy to accelerate to c. But why is there a maximum at all? And why that particular value, 300 million meters per second? Space-time itself has structure. That structure determines c. It's like sound. The speed of sound in air is determined by the air's properties: density, pressure, temperature, the mass of air molecules. Those properties fix how fast a compression wave can propagate through the medium. Same with spacetime, except there's no medium. Spacetime isn't made of anything. It is the thing. But it still has properties. Suppose spacetime is like a fabric with a certain stiffness, a certain resistance to disturbance. That stiffness sets how fast any disturbance can propagate through it, how fast information can travel. Electromagnetic waves, which include light, radio, waves, X-rays, propagate through this spacetime at c, not because light is special, but because spacetime has this fundamental speed limit built into its geometry. Light simply travels at the maximum possible speed because it has no mass to slow it down. And here's the surprising connection. Gravity also travels at c. Gravity isn't instant. If the sun suddenly disappeared, it won't. But imagine, we wouldn't know for 8 minutes. The Earth would continue orbiting the sun's former position for 8 minutes, the time it takes for the gravitational change to propagate across space at c. When massive objects accelerate, say, two black holes spiraling into each other, they create ripples in spacetime itself, gravity waves, disturbances in the geometry of spacetime. These ripples spread outward at c, like ripples on a pond, except these are ripples in space and time. We detected them in 2015. On September 14th, two black holes collided 1,300 million light-years away. They'd been orbiting each other, spiraling closer, for millions of years. In the final fraction of a second, they merged. The collision was so violent, it released more power than all the stars in the visible universe combined for that instant. Not as light, as gravitational waves, as vibrations in space-time itself. Those vibrations traveled at c through the universe for 1,300 million years. They reached Earth on September 14, 2015. Two detectors, one in Louisiana and one in Washington State, measured the tiny distortion as the wave passed through, a distortion smaller than the width of a proton, stretched across 4 kilometers. We measured it, matched the theoretical predictions, worked out from general relativity to extraordinary precision. In 1916, I predicted these waves mathematically. The equations said they must exist, but I thought they'd be far too small to measure. I wrote in a letter, "It is doubtful that we will ever observe them." I was wrong about that. The universe is more violent than I imagined, and our instruments became more sensitive than I dreamed possible. What this tells us, space-time is unified in a profound way, not a separate stage where events happen, where matter moves around against a fixed background. Space-time is an active participant. It curves, it ripples, it determines what's possible. The speed limit, the conversion between space and time, the way gravity works, the way matter and energy interact, all emerge from one underlying structure. Back to you, sitting there. You're not standing still. You're moving through space-time at c, just like everything else. Always, a fundamental law of nature. All objects move through space-time at the speed of light. When you walk across the room, you redirect some of that motion. Less through time, more through space. But the total stays c. You're always moving at light speed through the 4-dimensional fabric. You just change the direction. This means your rate of aging depends on your path through space-time. Not absolute. Relative to other paths. A twin who travels fast through space ages less than you, who stayed relatively still. Both of you experience 1 second per second locally. Time feels normal to each of you, but when you compare watches after the journey, the totals differ. The traveling twins watch shows less elapsed time. The future is not a fixed destination you're moving toward at a fixed rate. It's a dimension you're moving through at a variable rate, depending on your motion through space. How fast you age depends on how you move. This is why we cannot simply say now for the universe. Your now, the set of all events happening simultaneously from your perspective, is different from someone else's now if they're moving relative to you. Events that appear simultaneous to you occur at different times from their perspective. Simultaneity is relative. Time is relative. Only the space-time interval between events, the invariant combination of space separation and time separation, is absolute. The interval has a precise mathematical definition: the time difference squared minus the space difference squared in appropriate units. That number is the same in all reference frames. Everyone agrees on that. But the split between how much time and how much space depends on your motion. Not that time is an illusion. Time is real, but it's real the way position is real. Relative. You can't meaningfully ask your absolute position in the universe. Position relative to what? Relative to Earth? Fine. You're here. Relative to the sun? You're there. Relative to the center of the galaxy? Somewhere else entirely. Same with time. You can't meaningfully ask the absolute time. Time in whose reference frame? Relative to what state of motion? What's absolute is the geometry of space-time itself, the structure that determines how space and time trade off. The structure that sets c as the universal conversion factor between distance and duration, between meters and seconds, between space and time. So you see, you're always traveling through space-time at light speed, aimed mostly at the future when you're still in space, redirectable by moving through space, but never stopping, never slower, never faster than c through the unified whole. But this raises a question. Why is space-time four-dimensional? 3 dimensions of space, 1 of time. Why that split? Why not 5 dimensions total? Or 2? Why 3 spatial dimensions? Why can we move freely in 3 independent directions, but not 4? Why 1 temporal dimension? Why does time have a direction, past to future, while space doesn't? These are open questions, deep questions. Something about the stability of orbits, perhaps. In more than 3 space dimensions, planets wouldn't have stable orbits. Inverse square law wouldn't work the same way. Or something about the nature of forces, the way waves propagate, the structure of matter. For now, you know this much. You're moving. You always have been, even when you thought you were sitting still.